Hello students, I am Srihari. I am part of CurioSphere Academy. I'm here to solve your doubts regarding physics and mathematics. Okay, this is a demo class, so we will be solving certain questions from the class 12 chapter of atoms and nuclei. It's a moderate chapter. Sometimes it appears to be a more easier chapter too. So look, my point is, you understand the concept by doing the questions. You get the basic idea first by reading some of the concepts, and then you build the concepts by doing more and more questions. So how will I be going on with the things is, I will take a question, explain the concept behind it, and then we will solve it. Okay. I have taken mostly PYQs from various exams like JEE, NEET, Olympiads as well. So we will go through them one by one. Okay. Now come on. First question. The energy of the first excited state of helium plus ion is. Now, before starting any question, we have to focus on three things. First, what is asked in the question? What is asked in the question? What is given in the question? Okay. And like if you connect with these two, okay, what is asked and what is given, to bridge this gap, we need to find the concept behind the question. Sometimes there will be a single concept, sometimes there will be multiple concepts. Okay, once you get hold of what concept it is, you should get hold of the formula immediately. Okay, the formula. And once you get the formula, you just apply it to find the answers. For conceptual questions, the formula is not required, but a deep understanding of the concept is required. Okay, so for any question, to solve any question, these three parts. First, what is asked, then what is given, then what is the concept behind it, and eventually will lead to the formula. Okay, now let's go through this. Now, the energy of the first excited state of helium ion is. First, what is given? It is a helium plus ion. And what is asked? It is the first excited state. Energy is asked. Okay. Now, what is the concept behind it? Now, let's see this. Have you learned about Bohr's atomic model? You must have. It is a very popular model. You know, it revolutionized the field of physics, atomic physics especially. Like, you know, scientists have been trying to get the idea of the structure of atom for many centuries. First it was Dalton, right? Then it was Thomson, J.J. Thomson, right? Then it was our Rutherford. You know, Dalton, what his mistake? He didn't know there are subatomic particles. He considered atoms to be solid spheres. J.J. Thomson, what he did? He discovered electrons, but he gave the plum pudding model. Okay, plum pudding model, stating that all those atom was a sphere, like a solid sphere with the positive energy spread all over it, and the negative electrons being like puddings, like the plums on the puddings, like similar to a watermelon. The seeds of the watermelon are nothing but the electrons. But this again was failed, because Rutherford proved that most of the in his alpha particle scattering experiment, most of the alpha particles got undeviated. Okay, got undeviated. So the J. Thomson's model failed. Why did Rutherford's model fail? According to Rutherford, what he told was, if this is the center, positively charged center of the atom, the electrons move like in a planetary motion, similar to the planets around the sun. Okay, similar to the planets around the sun. But what, according to the classical physics, the classical definition of physics, if a body is revolving around a certain another body, it should continuously lose energy and eventually fall into the center, and the atom should hence collapse. But that is not the case, it is not happening. So Rutherford model also failed to explain it. But who explained it correctly was Bohr. What Bohr did differently is that he introduced the quantum element, right? He introduced the quantum element to the structure of atom. To the structure of atom. Earlier, every other scientists were trying to say or were believing that the energy of the electrons were continuous, meaning that they would eventually, the energy would decrease and come to zero and fall into the center. But according to quantum physics, energy is discrete or quantized. Energy is discrete or quantized. This was brought down by Max Planck's quantum theory, or Planck's quantum theory. Right? This element of discrete energy or quantized energy proved or explained that electrons in a particular orbit do not gain or lose energy unless or until they move to other orbits. Do not lose or gain energies unless they move to other orbits. Right. Now, electrons do not lose or gain energy unless they move to other orbits. And these discrete energy or the quantized energies are not just random values, they are multiples of h by 2 pi. H is called the Planck's constant. Usually, this entire term is denoted by h bar for simplicity. Okay, h bar for simplicity. Now these are the postulates. Now we go on to the postulates of Bohr's atomic model. Okay, the first postulate is that, as I already told you, he explained that the centripetal force for the electrons, mv squared by r, where v is the velocity of the electrons and r is the radius of orbit of the electrons. Okay, is equal to, or it is given by, the electrostatic interaction between the nucleus, the positively charged nucleus, and the negatively charged electrons. Remember the Coulomb's law? kq squared by r squared, where k is nothing but 1 by 4 pi epsilon naught. And here the charge of proton and electron are the same. Okay, now what to say? The charge of a proton, Ze. Wait, sorry for the pen thing, guys. Ze, charge of a proton, because number of protons depends upon the atomic number. Basically, atomic number is nothing but the number of protons inside the nucleus, right? And electron is the charge of is the charge of a single electron divided by r square, the distance between them. Now, if you can, this is one relation. This is very important. You need to remember this. This is the first relation, right? Second postulate is, I have already told you, it is the energy or the quantized energy must be, the energy of the orbits must be multiples of h by 2 pi. Only then they are allowed. Like the orbits which have their angular momentum, which is the rotational form of linear momentum, is multiple of h by 2 pi. This is another relation. Based on these two relations, Bohr was able to bring in a lot of let's say the velocity of electron in nth orbit, the radius of electron in nth orbit, right? You just need to substitute stuff. Okay, you need to substitute stuff. For example, for finding the velocity of electron in the nth orbit, right? From this equation 1 and 2, 1 by 4 pi epsilon naught z e squared r, we take the first thing, right? First equation, you cancel r on both sides, so mv squared equals to 1 by 4 pi epsilon naught z e squared by r, right? 1 mv squared. Now this mv, right, this mv can be written as, mv squared can be written as mv into v equals 1 by 4 pi epsilon naught z e squared by, oh my god, wait, z e squared by r. Instead of mv, can you see, you can substitute nh, oh my, one minute. Oh, this is not going. In h by 2 pi, right? Instead of mv, you can substitute from equation 2 nh by 2 pi r. nh by 2 pi r equals 1 by 4 pi epsilon naught z e squared by r. Now if you cancel r on both sides, right, and you don't forget the v here, right? You don't forget the v here. Now v, this implies v is equal to 1 by 4 pi epsilon naught e squared into 2 pi by h z by n, right? Z by n. If you notice clearly, all these are constants and we assign it to be v naught. Now v is equal to v naught z by n. This is our relation. This is the number of orbit, this is the atomic number of the atom or the nuclei, and this is the constant v naught. The value of this constant, by calculating this substituting everything here, you will get it as 2.2 into 10 power 6, 2.2 into 10 power 6 meter per second, or c by 137 meter per second, which is nothing but, c is nothing but the speed of light, as you know, right? Similarly, if you substitute for various things, you will get the value for r to be 0.53 into z square by n square angstrom units. Sorry, not z square by n square. I'm so sorry, my bad. R is equal to r naught into n squared by z. It is n squared by z, and this r naught is nothing but 0.53 angstrom units. .53 angstrom units r naught. Okay, r is equal to r naught into n squared by z. Similarly for energy, right? Similarly for energy, if you wish, here you have to apply the principle of conservation of energy, right? Principle of conservation of energy. E, you will get after like total initial energy equal total final energy or loss in kinetic energy is equal to gain in potential energy, in that way, right? The total energy of the system, kinetic energy plus potential energy, is equal, like what to say, the total energy system is nothing but the kinetic energy of the electrons plus the potential energy between the nucleus and the electrons, that is the electrostatic potential energy. And you will find out it to be n squared by z squared E naught. This E naught is nothing but minus 13.6 electron volts. Mostly energy is measured in electron volts, right? Mostly energy is measured in electron volts. In other sometimes you may be asked questions to convert this electron volt to joules and some like other units as well. In that case, you have to find the relation, how much joule is 1 electron volt. So before exams, all these conversions you need to get a hold of it. Okay. Now coming, this is all about what's a Bohr's model. Still there's stuff in Bohr's model. We'll talk about it regarding the time period. Right, time period, you know na, like time period is nothing but time period of revolution. You know what that time is distance traveled by velocity. Now distance travel is the electron travels one whole revolution around the nucleus, right? One whole revolution around the nucleus, that is the circumference of the orbit 2 pi r divided by the velocity v. Now velocity of nth orbit you have here, right? You just substitute it here and you will get it. Instead of v naught, 2 pi r upon, this is radius of nth orbit, nth orbit, just for the convenience I am keeping it nth orbit, and this is v naught z by n, right? v naught z by n and rn is nothing but r naught, right? 2 pi r naught into what is it, what is r naught into n squared by z, right? N squared by z upon v naught. This n z by n will go at n by z right? Z by n will go as n by z. It will be, this is total a constant, it is t naught n cube by z square. T is equal to n cube by z square. You need to remember all these formulas so that while going into the examination hall, you will, what to say, if you just remember, you see the question, what is given, what is asked, remember the concept, Bohr's model, and you will get directly to the formula. You can just apply the formula, right? You can just apply the formula. Still, as a few things are left with the what to say, Bohr's model, the frequency, the wavelength, right? The what to say, the Rydberg's constant, etc. We'll deal with those in the upcoming questions where these concepts will be required. So now we'll go ahead solving the question. Wait 1 minute. Right, I'm just making it smaller. Yeah. Now, come on guys. The energy of the first excited state of helium plus ions. And one more thing. Do you think Bohr's model was all successful? No. Bohr's model was applicable only to hydrogen or hydrogen-like atoms. What do you mean by hydrogen-like atoms? How many electrons are there in a hydrogen atom? 1 electron. How many neutrons are there in one hydrogen atom? A normal hydrogen atom, 1, right? Is it 1? No. It doesn't have a neutron. 0 neutrons, 1 proton, because a typical hydrogen atom is a 1H1 hydrogen atom, which is the mass number is 1, the atomic number is as well 1. Okay, so, and what about a helium plus ion? What is a normal helium atom? Is depicted by 4, 2. What is this actually? It is the mass number. This is the atomic number. Now mass number is nothing but number of neutrons plus number of protons, right, which is 4. In a helium plus ion, right, in a helium plus ion, helium plus, what do you, when a charge comes over an atom, what does it mean actually? It means it has lost a negative charge, right? It has lost a negative charge. It has lost an electron. See, basically a normal atom, the number of protons is equal to number of electrons. So how much ever a positive charge is there, there is an equal amount of negative charge. So normally an atom is neutral. What? A neutral. But when you lose an electron, it is not because you are losing an electron, not directly because of loss of electron you get a positive charge. It's because as you lose one electron, the total positive charge is greater than the total negative charge, so the net charge comes out to be positive, right? This is positive, this is negative, so the net comes out to be positive. This is how you get positive ions. Now coming back to helium plus, its mass number remains the same because there is no change in the nuclei, but the electrons, it is a one electron species, right? It is a one electron species similar to hydrogen. So whatever we see similar to hydrogen or hydrogen like atoms is nothing but one electron species. They are nothing but one electron species. Right? Now coming back to the question. So simple, helium plus ion is nothing but hydrogen ion. So we can apply Bohr's model. And one more thing, you should not just blindly go behind the concept. You have to check whether for the given case does the concept is applicable or not. Right? Sometimes if they give just helium ion, like helium atom, you cannot use Bohr's model because it's not a one electron species, right? Why do you think Bohr model does not come into the picture when the number of electrons becomes more? Because the inter-electronic repulsion start taking place, shielding effect takes place. Due to this, the radius of the electrons, the orbits change, and much more things also will change, right? So yeah, just then the same phenomena happens in interplanetary things as well, but let's not dive into that now. Let's focus on this question. Bohr's model can be applied. Okay, now what is it for? What is the formula? Now I have to remember the formula. I have got the concept. Now to remember the formula. What is the formula for the energy of nth orbit? E is equal to minus 13.6 like 13.6. What is the factor? Z square by n square, electron volt, right? Now coming back, it is 13.6. What is Z for helium? That is nothing but the atomic number, right? Minus 13.6 into Z is what? 2 squared. Wait, 2 squared, 2 squared, and n squared is nothing but the orbit number, 1 square. If you substitute and if you calculate it, you will get, wait, let me check, minus 13.6 into 4, minus 54.4 electron. Well, yeah, that's the option D, minus 54.4 electron volt. That is option D. This is a J main 2023 question, guys. It's a J main question. It's a very simple question. It took time because I was explaining you all the concepts and stuff. I believe in this. You go to the question, think of the concept, you go learn the concept, then you go back to the question, you'll get a much more clarity rather than just reading the concepts continuously. Okay, wait, let us check the answer with the answer. Wait 1 minute. Meanwhile, you just keep reading this question. I hope it's a very easy question. It's be correct. wait, we made a mistake. First, see, this is where we make the mistake. This is where we make the mistake. See, it does not say first shell. It says the first excited state, which means, see, the atom, the nucleus is here. It's the n is equal to 1, n is equal to 2. Always the first thing is the ground state. This will be this excited state. This cannot be never be excited state because below this there is no orbit, but this can be like excited state because below this there is the first orbit. Okay, so the first excited state means n is equal to 2, n is equal to 2. This is where we make mistakes. Read the question carefully. So n is equal to 2 in the sense z square by n square is equal to minus 13.6. 2 squared by 2 squared, that is, we get cancelled, and yes, minus 13.6 eV. So the answer is A option. Sorry guys, I just didn't notice it, but don't make this mistake in the exam. Okay. Yeah. And if you notice, hydrogen's first orbit energy and helium ion second orbit, the first excited state energy, is the same. Can you interpret anything from this? If so, you can reach out to me and say it. No issues. Now, coming back to second question, which of the following is true about nuclear density? Right, nuclear density. Yeah, here they are like given a concept of nuclear density, and they are asking which of the point go related with the concept. In this question, instead of focusing on the formula first, you just read all the options, intuitively try to select the questions answers which you seem to be true for you. Nuclear density decreases with mass number. First of all, what is nuclear density? What is density? Density is nothing but mass by volume, right? Mass by volume. Or nuclear density means the mass of the nucleus, that is nothing but the mass number, or divided by A, mass number, divided by the volume of the nucleus, right? This is A by V, volume of the nucleus, right? Now, nuclear density increases with mass number. If we keep volume constant, as mass number increases, density increases, right? So this might be true. We are not sure. Let's check it out. Nuclear density decreases with A. This is definitely false because nuclear density is directly proportional to A, right? This is definitely false. Now, nuclear density is approximately constant for all nuclei. This can be true, may or may not be true. Let's check it out. Let's skip for that. Heavier nuclei are more densely packed. This also seems to be true, right? This also seems to be true. Now, by intuitive way, we are able to rule out only option B. So now our intuition doesn't work properly. So we should go back to what the formula. Using the formula, we need to do it. Do you all remember that the formula for atomic radius R is equal to R naught into A power 1 by 3. Do you all remember this formula? I hope you all remember this formula, right? It is giving the radius of a nuclei in terms of the mass number. It is giving in terms of mass number. R naught is nothing but a constant, right? A constant. I don't know in which chapter you have learned, but surely you must have learned that there are four kinds of there are a few kinds of forces, right? The gravitational force, strong nuclear force, weak nuclear force, such forces. In that, the strong nuclear force happens to be existing only within a specified dimension or a specified distance, range of distances. I don't know, about approximately 10 power minus 15 meter to 10 power minus 14 meter, but yeah, whatsoever it is, strong nuclear force, we know it exists in between the neutrons and the protons inside the nucleus, and their range is between 10 power minus 14 to 10 power minus 15. So we can say that atoms, they don't have, every nuclei, they do not have the same radii, but they can, what to say, they be compared, like not approximately they must be one and the same when it comes to heavier nuclei at least. So okay, let's come to the formula directly. Okay, R is equal to R naught A power 1 by 3, where R naught is a constant and A is nothing but the mass number. Now what is the formula? Basically nuclei is a sphere, right? What is the volume of a sphere? Formula 1, P is equal to 4 by 3 pi R cube. Here R is nothing but R naught. I'm just using the small letters, right? R naught cube A, right? R naught cube A. And what is the mass? Mass is nothing but the number of neutrons plus number of protons, nothing but the mass number A. Now if you substitute this in the formula of basic formula, density is equal to mass by volume, you will get A by 4 by 3 pi R naught cube A. You will get it as a constant, right? You will get it as some constant. Density used to be some constant because it's 1 by 4 by 3 pi R naught cube, everything is a constant. So density is approximately constant because see, R naught is a constant of proportionality, but every atom has its own, like some places number of neutrons are more than number of protons, so nucleus is unstable and it may expand or contract, radioactive decay may happen, right? So this is only approximately constant, right? It's only approximately constant. If you have further doubts, you can come out to me. So our answer is option C, right? Our answer is option C. This is JEE Main 2022 question. Now coming out to the average nuclear density, the same thing, the average nuclear density, right? It is from H.C. Verma. This question is from H.C. Verma. Guys, for physics, H.C. Verma is very good book. I know you need not know what is it, like you already know this, so I'm just saying. Estimate the average nuclear density in kilogram per meter cube, right? In kilogram per meter cube. Now just now we derived the formula for density, right? Average density is nothing but density, simple, just calculate the density now, right? This one, wait, you bring this to the numerator, density, or you can have it as a row, okay? Instead of D, you can have it as a row if you want. 3 by wait, rho is equal to 3 by 4 pi R naught cube. 3 by 4 pi R naught cube. I think there's a term missing here. Average nuclear density. Guys, we made a small mistake in the previous question, that mass is not directly equal to mass number. It is, see, mass number is nothing but the number of protons and neutrons, and the mass of neutron and the mass of proton are approximately same. So if we take the small m, mass of a nucleon, mass of a single particle, into the number of particles, this is actually the total mass, right? This is actually the total mass, and this one is wrong. Actually, this is wrong. So if we consider this in the formula, D is equal to ma by 4 by 3 pi R naught cube A will get cancelled, everything else is a constant, so D must be equal to 3m by 4 pi R naught cube. we are substituting this formula. D is equal to 4 by 3 by 4 pi r naught cube. In the numerator there is an m, mass of a nucleon, right? Mass of a nucleon. Substituting all these values, 3 into, what is the mass of a nucleon, right? What is the mass of a nucleon? Approximately it is 1. They're asking in kg, so we have to give in kg. 1.6 into 10 power minus 27 kilogram divided by 4 into, what is by 3.14 into r naught cube. What is the value of r naught? And constant in meters is 1.2 into 10 power minus 15. 1.2 into 10 power minus 15, right? And if you substitute, you will get the answer to be D is equal to, or rho is equal to 10 power 17 kilogram per meter cube. D or rho is equal to 10 power 17 kilogram per meter cube. Answer is this. This is a HC Burma question actually, from HC Burma exercise, right? Well, coming back to the question number 4. Question number 4, a radioactive substance has a half-life of 30 minutes, right? Now we have to go back to what? Radioactivity. Radioactivity actually comes in chemistry, chemical kinetics. Though you're not studying so much about radioactivity over there, but you still have radioactive reactions, and they're always first order reactions. Do you remember? All radioactive reactions are first order reactions, meaning that their order is n is equal to 1. Order n is equal to 1, right? So for first order reactions, you know the formula, T half formula, or directly write T formula first, so that from that T is equal to 1 by K, where K is nothing but the rate constant. T is equal to 1 by K ln A by A minus X, right? A naught is the initial amount and X is the amount it is decayed. X is the amount which is decayed. Now this is the formula. See, since we have seen that it is a radioactive substance, we got the concept that it is a first order reaction. Actually, you will learn this, all the first order reactions, all differential equations. It's also mathematics, so that's a mathematics course as well. If you come to ICER, the first year, in the second semester, there is a mathematical course on differential equations. You will learn all this in maths as well. In chemistry also, it will be applied in the same semester, right? In chemical kinetics, radioactive substance half-life, T half. Now tell me, what is T half? Half-life is nothing but what? The time taken for the radioactive substance to reduce to its half of its mass. Okay, T half. So like if it is T half, X must be A naught by 2, right? X must be A naught by 2. So T half is equal to, I'm sorry with this pen, this is T half is equal to 1 by K ln X is 1 by 2, A naught by 2, A naught minus A naught by 2 is nothing but A naught by 2. So A naught by A naught by 2, A naught will get cancelled. So T half is equal to ln 2 by K. ln 2 by K, right? This is the formula. And what is T half given as? 30 minutes. So you get 30 by ln 2 equals 1 by K. Now keep it this to be 1 by K itself. Actually, for convenience, you will get to know in a while. 1 by K is equal to ln 2 by 30. Oh sorry, wait. 1 by k is equal to 30 by ln 2. Now coming back, you substitute this formula. Do you see here this one? This formula, they are asking for the time for after 90 minutes. Now in such cases, they give the value for one particular thing and they are asking for the value for another thing. For half-life, they have given the time. They are asking how much amount substance will remain after this much amount of time. So in this case, you have to use the same formula used for two different cases. In one case, time is given and the amount of substance that is also given. Using that, you need to find the constant in the reaction, in the formula. Using that the constant, the formula you have to apply for the unknown case, which is 90 minutes here. So the constant 1 by k. So since why I told 1 by k, because here it is here we have 1 by k, so we directly substitute 1 by k with 30 by ln2. So now t is equal to 30 by ln2 instead of 1 by k, and ln a naught by a naught minus x, ln a naught by a naught minus x. Right, now what is given as t is 90 minutes. 90 equals 30 by ln2 ln a naught by a naught minus x. Now you cancel it, 3, right? You get ln a naught by a naught minus x equals ln2. Just you can take off the ln or take exponential on both the sides, you will get the same thing. A naught by a naught minus x equals a naught by a naught minus x equals 2, right? If you shift that side, a naught cross multiply 2a naught minus 2x, right? 2x a naught minus a naught is equals to 2x. Oh wait, we forgot there is a 3 ln here. See, there's a 3 here. 3 ln2 will become ln 8. See, 3 ln2 is nothing but ln 2 cube, that is ln 8. Right, now you cross multiply a naught by a naught minus x equals to 8. Cross multiply, you get a naught is equals to 8 a naught minus 8x. Now you get 8x is equal to 7 a naught, x is equal to 7 by 8 a naught. Now what is x? It is not the amount remaining, it is amount decayed. So to find that amount remaining, what is the initial amount a naught minus how much it is decayed, 7 by 8 a naught, so which is 1 by 8 a naught, which is the answer is option C, JEE Main 2021 question. Right, and there is another shortcut way. See, sometimes these long methods will be helpful if you don't have the patience to think for a shortcut method. You can just go for the traditional method and complete it quickly. But if you get such questions in the beginning stage of the examination itself, you could go some shortcuts, easy shortcuts. Like for example, what is a t half? What? In 90 minutes, so the t half is 30 minutes. Now see, this is the reaction, right? This is a naught. In 30 minutes, it becomes a naught by 2. And in how much time? It will be what will be the amount left in 90 minutes? If 30 minutes is the t half, 30 minutes the t half, in how many half-lives are there in 90 minutes? See, the time required for us is 90 minutes. T half for us is 30 minutes. How many 30s are there in 90? 3, right? 3. And 1 by 2, 1 by 2 is a standard notation, 1 by 2 whole power n, where n is nothing but number of half-lives within the time frame we need. Okay, number of half-lives within the time frame we need. Here it is 3, because 3 times 30 gives 90. Okay, so it is 1 by 2 whole power 3, that is 1 by 8 shortcut. But this is applicable only if there is if the half-life is a factor of the asked time. For example, if it is 100 minutes, then we can't use this. If they ask for 120 minutes, we can use this 1 by 2 whole power 4. That case it will get. So the shortcuts are good, but it will work only for certain cases, right? Now question 5. The deuterium consists of proton, neutron. When separated, who has lesser kinetic energy? Now this is a classical example of a bomb exploding from inside, applying momentum conservation, right? Remember class 11 physics? There you apply momentum conservation, find which direction both the pieces of the object go, how much distance they travel, or you use momentum conservation and energy conservation basically, because there is no external force. It is exploding because of the force within. It's similar to that. Okay, this is similar to that. Deuterium consists of proton and a neutron. What is a deuterium? First, a hydrogen atom, normal hydrogen atom, consists of one proton and one electron. What a deuterium ion, right? The deuterium ion consists of two protons and one electron. It is the same hydrogen atom but with an extra neutron, one proton and a one neutron. The mass number is increased, right? So that is what a difference. It is a deuterium atom, deuterium nucleon, whatever you call it. Okay, so in a deuterium nuclei there is one proton and one neutron, right? One proton and one neutron. When separated, who has lesser kinetic energy? First of all, after separation, right, for momentum to be conserved, they must move in the opposite direction, right? They must move in opposite direction, because assume there is no external force causing it. It is happening just because of the forces within. The repulsive forces begin, for example. So one object, the proton should go in one direction, the neutron should go in another direction. So this is clear. This is momentum conservation. Now energy conservation. The total energy initially is equal to total energy finally, right? Total energy finally. Now this total energy finally, the total energy initially is given by the potential energy between the neutron and proton, right? The potential energy or the binding energy. The potential energy in this case is nothing but the binding energy. Let's talk about binding energy later when such questions arise. Okay, the binding energy is a more interesting term. It is used, it will help neutrons and protons to keep them together even though they have repulsive interactions between them. Now let's discuss about binding energy later, but for now it is potential energy. The total potential energy is given by the kinetic energy of the proton plus kinetic energy of the neutron, right? Kinetic energy formula, what is it? Half mv squared. But there is even another formula, p squared by 2m, right? P squared by 2m, where p is nothing but the momentum, right? The p is nothing but the momentum. P, for example, for convenience, p squared, that is for a proton, by 2mp plus pe squared, pn squared, that is for an electron, that is a neutron, right? And 2mn. Now we just need to find out which contributes more to the sum or which contributes less to the sum, right? This is binding energy, right? One minute. Yeah. Now total energy initially, total energy finally, 2mp, 2mn. Now compare the masses of neutrons and protons. Which has a higher mass? I think it's neutron, right? Which, 2 × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × 10⁻⁴ × Yeah, neutron has a slightly greater mass. You have to what to say, have all these relations: the charge of a neutron, the positive charge of a neutron, like a proton, and the negative charge of an electron. Magnitude, they are the same, and also the masses of the particles, subatomic particles. Mass of neutron is greater than mass of proton is greater than mass of electron. Electron is very very, light. Light. Mm, their mass of neutron is approximately same to the mass of mass of proton. Neutron and proton have approximately the same mass, but when it comes to electrons, it's very very small. It is very very small. So we have known that mass of proton is lesser. So if, for example, we are assuming momentum constant for both, momentum is constant for both. Okay, for now just assuming now the mass of proton is lesser, so this whole fraction is higher. The mass of neutron is higher, so the whole fraction is lesser. Okay, so the binding energy, if the momentum is the same for both, this gives a lesser contribution because the fraction comes out to be lesser. The neutron gives a lesser contribution. Now we need to just check whether the momentum is same for both. Okay, now you see the mass is almost the same, approximately the same. Okay, and they move in opposite directions for momentum to be conserved. So if the momentum of v, momentum of proton is minus v, the momentum of neutron will be plus v. But the momentum, the p squared term, this plus sign and positive sign and negative sign will not have any effect. So apparently, magnitude wise at least, p squared term vanishes the signs. So p squared of proton is equal to p squared of then neutron. So whatever we saw, it's true. Whatever we assumed is true. The momentum of both the particles is the same according to the law of conservation of momentum, for momentum to be conserved, right? So now we have to compare only the masses, and that we have found it already. This fraction of neutron gives a lesser contribution, right? This fraction of a neutron gives a lesser contribution, so the answer must be a neutron. Yeah, it's exactly a neutron. This is H.C. Verma conceptual question, but yeah, there's no heavy calculations involved.